Okay, good evening, everybody, or guess good morning. So today I'm going to go over 1.4 unit tangent, normal, and binormal vector. We already know what a tangent vector is, and now we have to know what it's meant by unit. We've talked about this a lot in math. Unit in math means one. So we're talking about a tangent vector that has a length of one. And then the same thing goes for a normal and a binormal vector. Okay, what's really unique about these is if you think about how this works out, say you have some sort of a curve in 3 space that looks something like that. What the tangent's going to be is it's going to look like this. That's going to be the tangent vector. The normal vector now it does depend on if it's 2 space, 3 space, but it's going to be perpendicular. Now, whether it goes into the curve or out of the curve, it kind of depends on the scenario. I'm going to go ahead and say it goes into the curve right now, and those are perpendicular to each other. So this is going to be the tangent vector, this is going to be the normal vector, and then the binormal vector is the vector that's perpendicular to both of those. So it'd be like it was coming out of the screen right at you. Okay, so it looks something like that, but this one is going to be perpendicular to those two. Okay, so first, unit tangent vector. So C is a graph of a smooth curve, vector value function, R of t and R2 or R3. Remember, R2 stands for 2 space, R3 stands for 3 space. Okay, that's what those represent. R prime of t is non-zero, then the unit tangent vector of the curve C at t is given by this equation. Now, if you think about what's happening here, is all you're doing is you're taking whatever that tangent vector is and you're dividing by its length. We think about what happens if you do that. If you took something that was of length 12 and you divided by 12, it would now be length 1, which would give it the unit aspect of it. Okay? So if you take a vector and divide it by its length, it will turn it into a magnitude of 1. So, for example, find the unit tangent vector of the graph, R of t, which is equal to this at the point when t is equal to 2. So let's go ahead and take the derivative. So I have R prime of t is equal to 2ti plus 3t squared j. Okay? And then we can evaluate it at R prime of 2. Well, that's going to be 4i plus 3 times 4, so 12j. Okay, so that's what that vector is. Now, hopefully you can see that that doesn't have a magnitude of 1. So let's go ahead and figure out what the magnitude of that is at 2. Well, that's going to be the square root of 4 squared plus 12 squared, which is going to give you the square root of 16 plus 144, which is the square root of, 160. I don't know. I mean, we could go a little bit further than that. I don't know if it's necessary to go any further than that. Hold on. I just want to make sure that everything's working out okay. Yeah, so let's go ahead and do this. This is going to be 4 times 40, which is 4 times 4 times 10. Square root of 4 is 2. 2 times 2 is 4. So this is equal to 4 times the square root of 10. Okay. So I want to know the unit tangent vector. So that's going to be given by this formula up here. So you have t of 2 is equal to r prime of 2 all over the magnitude of r prime of 2. So r prime of 2 is 4i plus 12j, and this is going to be all over 4 times the square root of 10. So this is going to give you I plus 3j all over the square root of 10. Of course, you could go a little bit further than that if you wanted to rationalize it, split it up, whatever, but there's nothing wrong with this answer, so I'm just going to leave it as is. Oops, sorry about that. You can't even see that. Okay. Okay, so that's the unit tangent vector. So now we want to go into the principal unit normal vector. So like I stated before, this is just going to be the one that's perpendicular to the tangent vector. So if C is a graph of a smooth vector value R of t, vector value function R of t and R2, R3, t prime is non-zero, then the principal normal vector to c at t is given by this equation. Okay? So you take t prime of t, which is the derivative of the tangent, then the principal normal, so it's given this, and you just divide it by the magnitude. Okay? So now in R2, the normal always goes into the curve. Okay, that's why I was giving you this example up here. I was careful to state that it depends on the system that we're working in, but if it is in R2, then it does go into the curve. Okay, so this is what the formula is. Okay, so find t of t and n of t for the circular helix. So the first thing I'm going to do is I'm simply just going to rewrite this in a vector value function form. So r of t is equal to a times cosine of ti plus a sine of tj plus c a of t. So then we have r prime of t is given as negative a sine of ti plus a cosine of tj. And then c is a constant. Where'd that c come from? This is written in, where'd that c come from? I'm a little confused what I did there. So this is ATK. I'm not sure what happened there. Sorry. And so then taking the derivative of this, I'm just going to get a K. Okay, so I need to find out what T prime is. And so I know R prime of T is, and I just have to find the magnitude of R prime of T. So this is the square root of this thing squared plus that thing squared plus that thing squared. So I have a squared sine of t squared plus a squared cosine of t squared, and then plus a squared. Factor out an a squared. So you have a times the square root of 1 plus 1, which is a times the square root of 2. Okay, so you take an a squared out of all these, you'll have a sine squared plus cosine squared, which is 1, and then you took an a squared out of here, so this just turns into a 1. 1 plus the 1 gives you the 2. Okay, so what I know then is t of t is equal to this thing divided by that thing. Okay, well, if you notice, all of these have an a to it. That has an a to it, so just cancel it out. So it's 1 over root 2 times negative sine of ti plus cosine of tj, and then plus k. Okay, so that's what t prime of t is equal to. Okay, so what about n prime of t? Okay, n prime of t. So now we're going to go ahead and use this formula here to calculate it. So I just need to take the derivative of the thing that I just found. So I have n of t is equal to t prime of t, so this thing. So I have 1 over root 2. This would be negative cosine of ti minus sine of tj, and then that clearly goes to 0. I'm going to factor out a negative. I don't even know if I need to. I'll just go ahead and rewrite this as negative 1 over root 2 times cosine of ti minus 1 over root 2 sine of tj. Okay, so I still have to find the magnitude. So this is what, that's just the t prime part. I still need to divide it by the magnitude of this thing. So the magnitude is going to, I'm just going to go ahead and use this one over here. So it'd be the square roots of this thing squared. So I have 1/2 cosine squared t plus this thing squared. So 1/2 sine squared t. You can factor the 1/2. So I have 1 over root 2 I'm with cosine squared plus sine squared, so I just get 1 over root 2. So this is 1 over root 2. And then you notice cancel, cancel, cancel. So my answer is just negative cosine of ti minus sine of tj. Okay, and there we are. Okay, next page. Okay, so compute t and n for the curves parametrized by arc length. So now it's a little bit different, right? If you notice before, it was t of t and n of t, and so our parameterization was based off of the parameter t. So now we have to be able to switch it because there's sometimes I want to come up with an equation that's in terms of the arc length, and so that's exactly what I'm going to do. I'm going to go ahead and come up with these equations. So these are what the equations are, and we're going to go ahead and prove these. Okay, so the first one is recall by theorem 1.3.5, and we just hit this really quickly at the end of the last class period, that the magnitude of r of s, r prime of s, is equal to 1. Okay, so because of that, you know t of s, by the definition, is r prime of s all over the magnitude of r prime of s. And we just talked about that being equal to 1, so it's equal to r prime of s. Okay, and that's that first portion I wanted to show right there. So now I just need to go ahead and do the second portion. So it's r double prime of s over the magnitude of r double prime of s. So also, what do we have? We have n of s, which is equal to t prime of s all over the magnitude of t prime of s. That's just by the definition we had before. But t of s is equal to r prime of s, so therefore t prime of s is equal to r double prime of s. And the same thing can be said for over here, so this is over the magnitude of r double prime of s. Okay? And there's that second portion. Okay. So the next one. Okay. So a circle of radius A with a counterclockwise orientation and centered at the origin can be represented by the vectored function this. You should know this already. Okay, this has come up, what, 3, 4, 5 times already? So you should know how to find the vectored value equation of a circle with radius A. Okay, there's the A, cosine, sine, and then that's going to simply be it. Okay. Oh, I left off the question. The question should say, find t of s and n of s. Okay, so r of s, if you recall from before, after it's been parameterized, is a times cosine of s all over a I plus a sine of s over a j. Okay, that was one of the very first things we did when we learned how to parameterize things. We learned what this parameterization was. Okay, just to step back for a moment, remember where this came from. We didn't use that magical formula. Remember, there's a magical formula that we had, the one with the integral and the magnitude. That's the one you're supposed to use. But if you remember for this one, we just said that the length is equal to r times theta, and then we changed it from there. Okay? If you don't recall, go back in your notes and look it up. It was at the very beginning of this parameterization 1.3 section. Okay, so that's what r of s is. So therefore r prime of s is equal to, okay, so the derivative of cosine is negative sine. And then the derivative of s over a, my variable is s, so the derivative is 1 over a. They're going to cancel, and I just left with negative sine of s all over a. I. Okay, same thing here. The derivative of s over a is 1 over a. The a's are going to cancel. So this is going to be plus cosine of S all over A J. Okay. Now I'm going to go ahead and I know I need the second derivative. Okay, so now that I know what the first derivative is, I'm going to go ahead and calculate the second derivative is. So we have to bring out the 1 over a now. So I have negative 1 all over a times cosine of S all over a I. And then minus 1 over a sine of S all over a j. Sorry about that, I'm writing off the paper. Okay, so this is minus 1 over a sine of S over a j. Okay, so now I need to find out what the magnitude of our double prime of S is equal to. So that's going to be the square root of this thing squared plus that thing squared. So I have 1 all over a squared times cosine squared of S all over a plus 1 all over a squared times sine squared of S all over a. Okay, factor out of 1 over a squared. So you're going to be left with 1 over a times, and you're left with cosine squared plus sine squared, which is just 1, so it's simply just 1 over a. That's what the magnitude of the second derivative is. Okay, so let's go ahead and let's find out what the things are. So T of S, by the formula what we had up here, is equal to R prime of S. R prime of S is just this. So I have negative sine of S all over a I plus cosine of S all over a j. Okay, that's what T of S is equal to. Now for N of S, I'm going to go up here and I'm going to utilize this formula. So R double prime of S, which is going to be negative 1 all over a times cosine of S all over a I minus 1 all over a sine of S all over a j all over the magnitude of R double prime squared, which we figured out was 1 all over a. Once again, look, everything, it cancels. Cancel, cancel, cancel. The negatives are still there. So N of S is equal to negative cosine of S all over a minus sine of S all over a, and that should be j, and that should be an I. Okay, and there we are. Okay, so now binormal vectors. Okay, so now I'm just going to kind of give you like a quick rundown of what it is. So if C is a graph of a vector value function R of t in R3, then we define the binormal vector at C, to C at t, to be the cross product. Well, you know that a cross product gives you a third vector that's perpendicular to the original two. So if the original two are t of t and n of t, then you take the cross product, you'll get back b of t. Okay? Note, b of t is orthogonal, that's the same thing as perpendicular, to t of t and n of t by the right-hand rule. Okay, we talked about taking the cross product. As you swing it up, wherever your thumb is pointing, that is where that vector is going to be going. Okay? And then the last theorem to calculate what b of t is, you have r prime of t crossed with r double prime over t, all over the magnitude of it. If it's the arc length parameter, then it's r prime of s crossed with r double prime of s all over r double prime of s, or the magnitude of it. Now, yeah, so I guess that's it, and then no proof is given here. Okay, so that was section 1.4. This will be due this Friday, as well as anything else, which I guess I'll have to deal with later. But that's it for now. So hopefully you guys understood this, and thank you guys for listening. And we will see you guys on Tuesday. Okay, bye everybody.